Hello and welcome to today's lecture on log periodic antennas. In the last few lectures we have been talking about Yagi-Uda and log periodic antennas. So, we saw that in Yagi-Uda antenna what we can do it is we can get a better gain by properly designing the directors, but we also saw Quasi-Yagi-Uda antenna where the emphasis on getting a larger bandwidth, but that bandwidth was of the order of 40 to 48%, whereas in case of log periodic antenna we can get much larger bandwidth compared to the Yagi-Uda antenna. So, we had started with the basic configuration of log periodic antenna, where we had seen that array of dipole antennas are there, and these arrays of dipole antennas were fed with equal and opposite phase. So, let us continue from here. So, just a quick revision. So, these are the dipole antennas, the length varies from L1, L2 to Ln plus 1, and then we had also seen that this is fed always from the lower end actually, and I will also explain here why we feed from the lower end. So, if we feed from the lower end, then we can see that at the lower frequency these will not get excited, the power will flow through here and this dipole antenna will get excited at the lowest frequency. As frequency of operation increases, then from here this dipole antenna will get excited, then this dipole antenna will get excited, then this dipole antenna will get excited, and so on. Whereas, suppose if we feed this thing from this side, so if we feed from this side, there are chances that higher frequency, this is supposed to be resonant, but at higher frequency there are chances that higher order modes may get excited. So, part of the power will be radiated through here and lesser power will there. So, in general you should keep a point that always feed from the lower dipole dimension only and not from the higher dipole dimension. Then the another thing we saw that basically the tau factor, which is known as a spacing factor, and we saw that the spacing factor is constant for R, L, D, even for the diameter and so on. And then from here we also saw the angle defined by tan alpha by 2, where alpha is given over here, half the angle is this, and we saw this expression over here. And then we looked at quickly the space factor. So, this is the space factor sigma, and this determines basically the spacing in this particular direction, and I had shown the quick steps. And finally, what we want to see is this is the relation where alpha is related to tau and sigma. So, now start the design procedure. So, let us say we need to design the antenna. So, we start with the lowest frequency and the highest frequency or the upper frequency. So, here the length of the first dipole antenna is approximately equal to the smallest lambda L here. I just want to mention lambda L is not small, L corresponds to the frequency. So, frequency is smallest, but lambda L will be the largest. Okay. So, please do not confuse, L is important over here, and so we start with this particular value. So, that will be the largest length and this will be the smallest length corresponding to the highest frequency. So, higher the frequency, lambda will be small. So, ln will be half of that. Now, you can see here this is written as an approximate, and you might wonder that earlier I had always mentioned take the dipole dimension as L plus D equal to 0.48 lambda, but here why we have written as lambda by 2. You can see first of all it is approximate. Second is that this antenna is very broadband. So, small shift in the frequency here and there will not make a difference. However, this is a additional thing which I want you people to really keep in mind when you are designing a log periodic dipole antenna. And what we want to tell you is that after this length here, so this is, even though most of the books tell you that you take this as L1, but what I am recommending is that you add one more large dipole behind this L1, which will act as a reflector to increase the gain at lower frequency. So, let us say in the figure what we are recommending is that you put one more antenna over here that can act as a reflector antenna. Now, sometimes people do ask, so whether the reflector antenna should be fed or it can be just put as it is. So if you use a Yagi-Uda concept, you can just put as it is, but if you want to use the log periodic concept, then this reflector antenna also can be cross coupled. Okay. So either of the possibilities are there. Then comes the next part, and that is the lowest one here. So the lowest dipole, what we again recommend, that add a few small dipoles in front, which will act as a director to increase gain. Again, let us just look at the figure back here. So what we are recommending is that after this dipole antenna, put some more element. The reason for that is, think about this, if we just choose this as the highest frequency dipole antenna, then there is a no director in front. Now apply the logic of the Yagi-Uda. So here is a one fed dipole, there is a one reflector. Having a multiple reflector does not make much of a sense. So it only has a one reflector, it does not have any director in front. So what will happen if you do not have a multiple elements in the front, then the gain will reduce at the higher frequency. So that is why it is our recommendation, when you are designing a log periodic dipole antenna, this can be the starting dipole and the ending dipole, but our recommendation is after that you add one larger dipole behind this and a few dipoles in front to increase the gain at higher frequencies. So now how do we do the design? So let us take the help of all the earlier researchers who have done a wonderful job, and they have given this particular directivity curve for different values of the directivity. So you can see here there is a 6.5 dB, 7 dB, 7.5, 8, 8.59 and so on. So let us say you want to design an antenna for directivity of, let us say, 7 dB for example. So if this is the case here, now you can see that 7 dB is constant for all of these cases, and what it is written here, that this is that optimum value. So how this optimum value is coming, or if you look at here 8 dB, so for 8 dB you can see, even though you can choose any point here, and what does it mean really, that any point? So let us say if I choose this point, so for this point if you draw the vertical line, it will imply tau is equal to 0.92, and if you look at the horizontal, that will be somewhere around 0.09. So you can choose this point, but that is not optimum. But this point if you choose here, what it shows here, if you draw the vertical line, that will give us a tau value which is close to, let us say, 0.86 or so, and if I draw the horizontal line, that will be around 0.16. So now why this optimum thing coming? I want to actually emphasize here what is happening by moving along this here, both tau and space factors are changing, and if you take along this thing, the most important thing what is happening is, I will just go back to the figure again. For that particular space factor, this distance is approximately equal to lambda by 2 at the region where this particular thing is more resonant, and then it will be lambda by 2 at the lower frequency region here. So when you choose this distance to be approximately lambda by 2, that satisfies a condition of end fire radiation better, okay, and that is how this optimum curve has come. Okay. So it is recommended that you choose the values corresponding to this optimum. I will also show you a one result where we have actually taken a value not over here, but somewhere over here, and then I will tell you also what are the pros and cons of that particular case also. So let us first go with this particular optimum design, and then we will see what happens if we do not take optimum design. So here this design is given in the book. So this is a design of 54 to 216 megahertz, but what I want to emphasize here, if you take the ratio is 1:4. So for example, if you want to design antenna from 1 gigahertz to 4 gigahertz, the similar concept will be available, just that starting and ending frequencies are different. So, here the requirement which was given as desired gain is 6.5 dB. So, since the desired gain is written as 6.5 dB, you take directivity curve of 7.5 dB assuming 1 dB loss. So, corresponding to 7.5 dB, let us just see where is 7.5 dB. So, this is 7.5 dB and that is an optimum point here. You can actually see from here, if I draw the line from here, that is close to 0.82, close to that, and if we draw the horizontal line, it is close to about 0.15. So, let us see what are the actual values. The actual values are 0.822 and 0.149. So, once we know tau and sigma from the directivity curve, we can now find the value of alpha, which comes out to be 33.3 degree. So, now the design begins. So, we start with L1. So, L1 is 0.5 of lambda L. This L is the lowest frequency, which is 54 megahertz. So, that comes out to be 2.78 meter, and corresponding to 216 megahertz, LU is 0.694. That means this is the dimension of the smallest dipole. So, now what we do, we start with this value and then let us see what we do. So, starting from this particular value, which is 2.78 meter, you multiply with this tau, and what is tau? Tau is equal to, let us see here, tau is equal to 0.822. So, you keep multiplying with 0.822. So, this one multiply by 0.822, you will get this here, multiply with this, multiply, continue this process till you have crossed this value, which is 0.694. So, you can see that you cross that value. Now, you can say 0.694, 0.705 are very close. Can we stop over here? Theoretically, you can stop over here, but then the gain at the higher frequency will not be good. So, that is why this element need to be taken. This will give us some decent gain. So, if you really count all of these elements, they come out to be n number. So, here we have found the length L1 to Ln. Now comes the next part, we need to find the spacing between the element. So, over here the spacing is given by this particular expression. Remember, this is a space factor, and by using this dn Ln, so for all values of L1 to this one you can find it. So, here are the spacing. Now, remember here, even though there are 9 elements, there will be only 8 spacing. So, between the 9 elements there will be only 8 different spacing. So, you can actually see again the figure. So, starting from, so if there are 9 elements, it will start from here 1, 2, and it will be the 8 spacing here. So, we got all the spacing. Now, what is not mentioned over here is the diameter. So, diameter, as I mentioned earlier, you can choose the diameter by given by a formula. Diameter should be equal to lambda by 100 to about lambda by 20. You can choose the value in between, you can choose the different values of that also. So, here are the results, but I want to mention this result is from 54 to 806 megahertz. You can see that this is a very large ratio. So, the ratio is more than 15. So, 1 is to 15, and these are the practical results. So, I will first talk about VSWR. So, you can see here, this is the VSWR2 line which is going over here. So, you can see that VSWR is less than 2, right, starting from 50 megahertz, even beyond 1500 megahertz also VSWR is less than 2. So, you can see that it has a very large VSWR bandwidth. Now, you can see here now the gain. So, close to 50, you can see that the gain is just about close to 3.5 dB or so, and then as we move up, you can see that the gain is close to 7 dB. So, one can actually see that the gain is good at this particular band here, but gain is not so good in this particular region. The reason for that is, for this particular frequency there is a no reflector behind, and since there is a no reflector behind, most of the radiation is going in the back direction. In fact, what we recommend that if you add another reflector, then what would have happened, that this particular curve, instead of starting from here, it would have actually started from here, and the whole curve would have been something like this. So, just by adding another reflector, we would have got relatively a constant gain over here. Now, let us just look at the radiation pattern and half power beam width. So, here it is a half power beam width of that particular antenna. You can see that this is a H plane and this is E plane. One can actually see that E plane half power beam width is shown along this axis and frequency is shown over here. So, one can actually see that E plane half power beam width is much smaller than the H plane beam width, which is very similar to the case of a Yagi-Uda antenna. I had mentioned that for H plane the dipoles are radiating in omni fashion, so which will have a broader beam width. For E plane the dipole radiate in the directional matter, and that is why half power beam width is smaller. So, now let us just look at another design example. So, I just want to mention here, in this particular design we have actually designed the antenna from 700 to 2500 megahertz. Just to tell you the reason why we chose this particular thing here, basically we had the requirement that we wanted to measure the cell phone tower radiation, and all these bands start from, let us say, 800 megahertz. So, for example, CDMA starts at 800, then GSM 900 is at 900, then GPS is 1500, then GSM 1800 will be 1800, and then we will have 3G which is 2100, then 2300 to 20, and then Wi-Fi around 2500. So, we had the requirement for an antenna which covers from 700 to 2500. So, since the frequency is known, you can also see the ratio is close to 1:4, well it is not exactly 1:4, 700 to 2800 will be there. So, here this design we have deliberately taken a slightly different case, where sigma is taken smaller than the optimum value to reduce the overall length of the antenna. Okay. So, just to show you what we have taken over here. So, tau is taken 0.89, sigma is taken as 0.083, and we will see that this is not really the optimum one. This is just to demonstrate you can take non-optimum thing also, but it is not really optimum in the real sense. So, you see that 0.89 will be somewhere here, and that is what is 0.083. So, that curve corresponds to this point here, whereas optimum value would have been somewhere here. But just to demonstrate the principle, but by choosing this value over here, what happens? Space factor is reduced. If we choose this value, space factor would have been larger. Okay. So, by taking a smaller space factor, what has been done? Spacing has been reduced. Okay. So, spacing in this direction, as it is, you can see along this direction, this is about 200 mm, along this it is about 280 mm, and this particular antenna has been fabricated on a low cost glass epoxy substrate. So, epsilon r is 4.4, tan delta is 0.02. Okay. And so, with this particular thing here, number of elements came out to be 20, because we had to cover the band right from 700 to 2500 megahertz. You can see one disadvantage, if you do not take the optimum, tau becomes larger. So, had we taken the optimum value, then tau would have been relatively smaller. Okay. And if the tau is small, number of elements would have reduced. So, it is not really always a good thing to focus on this number here, because if you focus on this number, then n increases. Okay. But nevertheless, this has been designed and fabricated, and as I mentioned, sometimes we learn a lot more if you do not do an optimum design, but I do not recommend this design for your future fabrication. Okay. Please stick to those optimum things, but let us see what are the results we get for this particular case here. So, here is the gain plot. you can actually see here the frequency 0.5 to 4 gigahertz, and this is the, you can see the gain value in terms of dB. Our requirement started, actually our requirement was around 0.8, because that is where the CDMA band starts. So, starting from here, if you see, gain is around 7 dB and at peak gain is around 7.7, and it is kind of decreasing, and you can actually see around 2.5 the gain is about 6.5 dB. So, if you really see, the gain variation is from 7 dB plus minus 0.7. This was not really of our band of interest. So, gain is actually reducing. So, why this is happening? Why gain is decreasing at higher frequency? The reason for that is that if you do not take this optimum value of the space, so what happens? This value has been taken much smaller, and if you take this value relatively smaller, then what happened? This is not effectively giving us a length of lambda by 2, whereas the feed is actually done in such a way that we are doing orthogonal feed. Let us just look at the feed, how the fabrication has been done. So, this is the PCB. On the PCB, you can see that this is the one feed line. On the back side also the same feed line is going on in the same fashion. Now, the dipoles are printed alternately. So, here you can see one half, this is another half, one half, then another half, and so on, and then this is printed on the back side. Now, what is done? You can see half dipole on bottom and this half dipole on top of the substrate, and now you can even see here that the feed is connected here. Well, that is not really correct. You actually see the coaxial cable is connected over here, but feed is not connected here. So, what we have done here, and that is what has been recommended in many books and papers. So, what we do for the coaxial cable, we remove the outside plastic jacket. So, that means if you remove the outside plastic jacket, it will only have the outer ground connector and there will be a center pin. So, that entire cable without the jacket goes over here, and the ground of the coaxial cable now, that is soldered underneath this particular thing, and then the center pin of the coaxial cable only comes out here. So, what we do, and there is a hole has been drilled over here, and the center pin is gets soldered at this particular point. So, that means feed is over here even though the connector is connected over here. So, here is a coaxial cable. I will repeat, coaxial cable is here, that coaxial cable outer jacket is removed, only the metallic portion is there. That metallic thing, which is a ground thing, is connected completely soldered all along this, and the center pin only comes over here, connects to the top line, and then you can see that all these things are connected to the top line and all of these are connected to the bottom line, and these two are at outer phase, and that is how the dipole antennas, it is maintained, it is outer phase. But now, as I mentioned, since it is not the optimum value of the sigma, so what really happens that the spacing between the two is not really lambda by 2 at the active frequency region. What is active frequency region? I will just mention that at the lowest frequency this one will excite and maybe little bit of this will excite. At the in between frequency, these will be excited. So, that means that will form the active region. At the highest frequency, these dipole antennas will be excited. Okay. So, that means as you increase the frequency of operation, so at the lowest frequency these will be active, as frequency increases, active region will actually move towards this. So, for any in between thing, for example, these will act as reflector, these will act as director. For this one over here, again all of these will act as reflector and all of these will act as director. So, by choosing this value here, what we have done, since the spacing has not been maintained properly, that is why you can see that there is a large variation in the gain. So, since our requirement was of the order of this here, it did meet the requirement. and we did fabricate this particular antenna also, and we want to now show you the measured results of this here. So, these are the measured S11 of the printed LPDA. Now, you can see this is the response here. Actually speaking, this is the reference line, which is 0 dB. This line here, which is not very properly visible, that is about minus 10 dB. One can actually notice that in between it has slightly crossed minus 10 dB line. So, we have defined here S11 less than minus 9 dB. Minus 9 dB corresponds to VSWR of approximately 2.1, which is acceptable for very large band antenna. And over here for this value, bandwidth is from 0.64 gigahertz to 3.74 gigahertz. So, you can see that in a very simple manner one can realize a broadband antenna with gain of around 7 dB plus minus 0.7 dB, which can be improved slightly, but you can see that the fabrication is very simple. You just take a glass epoxy substrate, print it on this, use a feed line. Be careful about the feed line, okay. I am repeating it that this is very important how you feed it, otherwise the radiation will not be proper. By doing this particular thing, then the radiation is of course in end fire direction. So, just to summarize then, we have talked about today log periodic antenna. So, we started with the very simple concept that you start with the lowest frequency to let us say the highest frequency, you choose the dipole antennas corresponding to the lowest and the highest frequency, but what we recommend that you add one larger dipole antenna which will act as a reflector, and you add a few smaller elements which will act as directors, so that you can take care of the decrease in the gate at the two end points. So, by using this scheme you can get relatively flatter gain over very large bandwidth. Then we looked at the design for a frequency range from 54 to 216. Then we saw the results for 54 to 806 megahertz, which basically covers the entire TV band from VHF to UHF, and we had also seen there the problem was the gain at the lower frequency was relatively lower, and I told you the solution. The solution would have been very simple, just put one reflector behind it, that would have given us a relatively flatter gain. And then we use the same concept to extend to cover the cellular bands right from 800 megahertz up to 2500 megahertz, and we looked at the simulated results as well as measured results. So, we conclude with that today's lecture, and in the next lecture we will talk about reflector antenna. So, several types of reflector antennas we will talk about. We will talk about plane reflector, then we will talk about corner reflector, and then we will talk about parabolic reflector antenna. So, with that, thank you very much. Work hard and do lot of design practice, and these are very useful antenna for several applications. So, do the practice and then do the simulation and fabrication. So, with that, thank you again. Bye.